So we're going to be looking at these over the next couple of lessons. For today, we're going to just start off with E and with A. We're going to be looking at finding limits when plugging in gives a finite number. So that happens both in this case and in the case of the piecewise functions. So just set these other three aside for a little bit. We'll come back to them in the next lesson. So here's a problem. Let's find the limit as x approaches 5 of x squared plus 1. So all we're going to do is we're going to take this 5, we're going to plug it in for x. 25 plus 1 is 26. That's a finite number. That's our answer. Done. Nothing more to it. That seems so easy. It went by way too quickly. Let's do another one. Limit x approaches 2. Let's do x plus 5 over x minus 3. So all I'm going to do, I'm going to plug that 2 in for x. Yep, really is that easy. We're done. Where it gets more complicated is if we have this situation. Let's say there's a limit as x approaches 3 of f of x, and we know f of x is 3x plus 1 if x is less than 3, and it's x squared if x is greater than or equal to 3. Now I notice that this matches those two, so we have a potential jump discontinuity. What that means, here, I'm going to bring these little arrows over here. What that means is it means we need to find the limit from both sides to see if it matches up. Because here's what could be going on. We could have a situation like this, where we've got one function here, one function here, and it's bad. That could be what's going on. Or we could have something, because there's a discontinuity, there's no overall limit. Notice that here we're looking for the overall limit. Or we could have a situation where it's something like this. Let's say it's going off like this, and we've got this other one coming up like here, but it just so happens that they have a point in common. This would mean that there is an overall limit because the left limit and the right limit are the same. Here there wouldn't be an overall limit. So if we want to find the overall limit of this one right here, I'm just going to point out, find overall limit. Then we need to find the left limit and the right limit and put them together. So if they're the same, the limit as x approaches 3 with no little plus or minus of f of x is the number they both equal. If not, if they don't match, limit as x approaches 3 of f of x does not exist. So let's find each of these pieces. This is still the same problem, number 3. So we need to find the limit of f of x as x approaches 3 from the left, limit as x approaches 3 from the right, and then we're going to have to compare those to get the overall limit. The problem we encounter, I rewrote what f of x was up here, is that I know that I want to plug in this 3, but I have two different equations. The question is which one I'm going to plug it in for. And the thing to remember about piecewise functions is that what's really going on is that we've got our xy coordinates. We're going to graph it. 3x plus 1, that's a line. X squared, that's a parabola. But we only want to graph this 3x plus 1 when x is less than 3. So that means that on this side of 3, less than left, we've got this function right here. It's over here on the left. Whereas when x is greater than 3, over here on the right, then that means that f of x equals x squared. So what we have to do, let's see, this is f of x equals f of x equals x squared. So I have to say, okay, if I'm approaching right over here, if I'm approaching 3 from the left, then I want to use the equation that's on the left hand, that's on the less than side. Notice these are always written from left to right when they're being written. So that means that this is going to be the same as the limit as x approaches 3 from the left of 3x minus 1. Because that's the one that's to the left of 3. So in that case, all I'm going to do is I'm going to take that 3, I'm going to plug it in for x. 3 times 3 is 9, minus 1 is, oops, it was plus 1, my bad. Plus 1 is 10. There's my left-hand limit. On the other hand, here I'm working with as we approach 3 from the right. So I want to use the function that's on the right. I want to use the function that's for greater than 3. So that means we're going to have the limit as x approaches 3 of x squared. And I'm still just going to plug that 3 right in there. Notice the limit as x approaches 3 from the left is not the same as the limit of f of x as x approaches 3 from the right. So the overall limit does not exist. Those are really the main ideas. We're going to just do a couple more examples with them, and then we'll be done with this lecture. Okay, so number 4, let's find the limit as x approaches 4 of g of x. And g of x, also a piecewise function, is going to be 2x if x is less than or equal to 4. It's going to be x plus 4 if x is greater than 4. So what that means, it means that if we were going to graph this function, or splitting it off at 4, when x is less than 4, so all the way over here, we have g of x equals 2x. And when x is greater than 4, off to the right here, we have g of x equals x plus 4. So because we have a piecewise function, we could have a jump discontinuity. So we have to check both the limit as we approach from the left. And if we do that, we're going to use the left side function, so that's 2x. So that's going to be 2 times 4 equals 8. And we also have to check the limit of g of x as x approaches 4 from the right. So we use the function that's on the right-hand side of 4, that's x plus 4. Notice in this case, the limit as x approaches 4 from the left is the same as the limit as x approaches 4 from the right, and they both equal 8. So the limit overall as x approaches 4 is 8. Sometimes these problems can be a little bit sneaky, like so many problems can be. Let's say we have this one. This is the limit as x approaches 2 of h of x. And we're going to say h of x is x squared plus 1 if x is less than 3, and it's negative 5x if x is greater than 3. Notice that when x equals 3, there is in fact no value at all. We have no equal signs here. We could have had something in the middle that says, okay, when x equals 3, there's this particular number. But all we care about with the limit is what we're approaching. So we actually don't care about what would happen if x equaled 3. And in this case, we really don't care about what happens when x equals 3 because we're evaluating the limit at x equals 2. So what makes this problem sneaky is that if we go to draw it, we've got h of x equals x squared plus 1 on one side. We've got h of x equals negative 5x on the other side. But when we go to do our left and our right limit, the number that we're looking at is actually 2. It's actually right there. It's wholly inside the domain that has this one. It's only when we are trying to find the limit at this number right here that we have to do the left and the right limit. Because on one side of 3, it's one equation, and on the other side of 3, it's the other equation. But here at 2, at 1.9 and at 2.1 on both sides of 2, it's still the same equation. So for this, all this is going to be of that pink one. So we can just plug that 2 right in, and that's our answer. We don't need to use both equations because the equations switch at x equals 3, and we're finding the limit at x equals 2 instead. Sometimes, like I was alluding to up here, we have a situation where we're saying, let's say, the limit of k of x as x approaches 4. And let's say that k of x actually has 3 different equations. Let's say one is 3x if x is less than 4, 2 if x equals 4, and 7 if x is greater than 4. Let's find the limit for k of x as x approaches 4. So what would happen if we were to graph this? So we've got this switch at 4. And on one side, less than 4 to the left, k of x equals 3x. Whoops, let's try that. There we go. K of x equals 3x. On the other side, when x is greater than 4, k of x equals 7. And then exactly right here, when x exactly equals 4, there's a little dot at 2. Just going to underline those in the colors. There we go. Now, the really key important thing we don't care. When x equals 4, we don't care what's happening. So we can really just ignore this one right here, because we're talking about the limits. We're talking about its hopes and dreams and aspirations. As it's coming from this side, it wants to be on the line 3x. It wants to be on the line that's going through right about like this. You don't have to be able to draw this, but I just want to show you what's going on. It's going like that. And let's see, when 4, it's going to be at 12, okay. And over here on this side, it wants to be on this line. It isn't right here, because it's not when x is greater than or equal to 4, just when it's greater than. But it wants to be on that line right there. So when we're looking for the limits, we're looking for, as we are approaching from the left, what does it want to be? As we are approaching from the right, what does it want to be? What it actually is, we don't care. This dot could be anywhere. So one very common error with problems like this is that students will go, okay, I want the limit as x approaches 4, so I say when x equals 4, f of x is 2, so the answer is 2. No, it's not. When we're doing this, when we have an overall limit, we have to do limit as x approaches 4 from the left, limit as x approaches 4 from the right. The only reason we didn't do that up here was because the number that we were finding the limit at was not the same as these numbers here. Here, the number we're finding the limit at is the same as these numbers here. We have to do both of them. So we're coming from the left, we're going to use the left equation. So that's going to be 3 times 4 gives us 12. This one we're going to use the right equation. It's just saying that it's 7. And notice here there is no x for us to plug in, so the answer is just 7. 7, no matter what x is, still 7. So when we're looking for the overall limit as x approaches 4, kx, because the left limit does not equal so the overall limit does not exist.